When we talked about electrical current, we said that current moves from a higher electrical potential energy to a lower one. We also defined the current as the flow of positive charges moving from the positive electrical potential energy to the negative one. In order for the charges to move, there has to be a force that puts them in motion in a specific direction. Such force will have to do some sort of work on the charges. The work done by the force can be translated in a change in energy of the charges. We define electromotive force, the ratio between the energy change of the charges and the amount of charges, or EMF equals delta U over Q. Note that, despite the name, the electromotive force is not a force in a mechanical sense. Instead, it is a potential energy per unit of charge, which we also call electric potential or just potential. The unit for the EMF is called volt, and it is the ratio between 1 unit of energy, or 1 joule, and 1 unit of charge, or 1 coulomb. Because of the measurement unit name, we used to call the EMF also with the name voltage. So the voltage is the difference of electrical potential energy that allows 1 unit of charge to move and produce a current. Be careful, though, that the voltage alone does not move the charges. The voltage is an expression of the potential energy of the charges. In other words, the voltage gives us an indication of how the charges would move if there was a medium that allowed them to do so. Think of a battery, for example. A battery is a device that provides us with a nominal voltage, for example 1.5 volts. But that does not mean that a current is flowing somewhere when in the presence of a battery. We need to connect the battery to an electric circuit to be able to generate a current. We need to attach conductors to the battery that brings the energy stored in the battery to a load. Then the current can start flowing. So the battery provides a difference in potential energy between its two poles, the positive and the negative. If we connect a load to the battery, by means of a couple of conductors, the potential energy of the battery is transformed in kinetic energy of the charges in the conductors, so the current starts flowing in and out of the load, like, for example, a light bulb or a motor. Finally, the kinetic energy of the charges is converted within the load in yet another kind of energy. For a light bulb, the energy is ultimately converted in heat and then in light. For a motor, the energy is converted into mechanical energy that puts the motor into motion. Like the current, we can say that there are two forms of voltage, the DC voltage and the AC voltage. The DC voltage is the one provided, for example, by batteries. It is a voltage of a fixed value and of fixed polarity. The plus and minus on the electrodes of the battery never change. One electrode will always be the positive one, and the other electrode will be always the negative one. So when we connect the battery to an electric circuit, we will have a flow of DC current. The AC voltage is the one created in the power plants and provided, for example, at the wall outlets in your house. The voltage at the outlet is not constant as the one in the batteries. Instead, it changes continuously following the shape of a sine wave. Because of that, the polarity at each electrode of the outlet changes over time from positive to negative and vice versa, following the shape of the sine wave. So when we connect a device to the electric outlet, the current that will flow through the device will be an AC current as well. The sinusoidal shape of the AC voltage depends on the way the electricity is generated. In the power plants, there are devices called alternators, a much bigger version of those that you can find inside your car to recharge the battery or in a bike to provide electricity to turn on the lights at night. Depending on the power plant, a different kind of energy is used to put in motion the alternator. It could be fossil fuel or nuclear energy that heat a reservoir of water and create the steam that makes the alternator rotate. Or it could be the rotation of a propeller-like device that is put in motion by the wind. Whatever the source is of the mechanical energy, the alternator converts that energy in electrical energy. But since the rotation translates into a sine wave when described on a Cartesian reference system, the resulting electrical energy acquires that shape too. But why do we need both forms of voltage, DC and AC? First of all, DC voltage is necessary to power any electronic device, from your TV to your smartphone or radio or computer. AC voltage, from the electrical engineering perspective, is used to transmit the electrical energy from the places where it is created to the places where it is used. Back to the time where the first experiments on electricity transmission were conducted, there was a famous diatribe between Thomas Edison and Nikola Tesla. Edison believed that the safest way to transmit electricity was to do that with cables powered with DC current. Tesla argued that it was better to use AC current because it allowed much less waste of energy during the transportation, thanks to the fact that it is easier to convert the voltage from a low value to a higher one, and vice versa, when using AC. And it is also very simple to convert the AC into DC when the DC is needed, through a process that is called rectification. Needless to say, Tesla won that battle, rightfully, and so today AC is used to bring the electrical energy to our homes from the power plants. Summarizing, to generate a current we need to provide some energy to the charges in the conductor. The potential energy per unit of charge is called EMF or electromotive force. That measures the capability of the generator, a battery for example, of generating a current. Most used synonyms of the EMF are voltage, difference of potential, potential, and tension. The measurement unit of the potential is the volt, which is the potential energy of 1 joule per unit of charge or 1 coulomb. The volt is a differential measure, not an absolute one. You always measure volts with respect to a point that we arbitrarily define as 0 volt or ground. EMF can be DC or AC, and correspondingly it can generate a DC or an AC current when connected to an electrical circuit. DC voltage is normally generated through chemical reactions in a battery. AC voltage is normally generated with alternators like those used in power plants. DC voltage can be easily obtained also from AC voltage through a process that is called rectification.